Okay, the next thing we need to talk about are chemical bonds, something that are very, very important, and they're pretty cool. And they're not too hard. It's pretty easy. A lot of you guys have probably already heard of a couple of the different types of chemical bonds. Maybe the covalent and the ionic ones, those are the big ones. Hydrogen bonds, maybe you haven't heard about van der Waals forces. I would almost guarantee you haven't. We'll just talk about them just really quickly, but there's something that you'll learn a lot more of to chemistry. So the importance of why bonds are so important is because they're what hold the atoms together and actually form molecules. That's why they're so important. We talked about before in the last set of notes that valence electrons, the ones in the outermost energy level, right? Those are the ones that actually form the bonds because they're the ones that are reacting with everything else. Bond energy is the energy required to break a chemical bond. So if it's a really strong bond, that means it takes a lot of energy to break it. If it's a really weak bond, it won't take very much energy to break it. Now the two types of strong bonds we're going to talk about are covalent and ionic, and that's what we're talking about next. Covalent bonds. Covalent. Co means to share, right? Valent is the outer energy levels, the outer energy level. So that's what it is. It's the sharing of electrons between atoms and to fill the atom's valence shell. Now, all atoms want to have filled valence shells. Now, we don't always have filled valence shells. There's this thing called the octet rule, which works most of the time. The octet rule is that the atoms want to have 8 electrons in their outermost energy level, or 2 if it's only the first one, remember, because the first energy level can only hold 2 electrons anyways. So this is for hydrogen gas, it can't have 8, but there's a good octet rule that they want to fill up that outer energy level, and usually it's with 8. When there are 2 unlike atoms, like, well, more than 2, if we have water, right, H2O, it forms a covalent compound. And then this is the example right here. A simple way of representing them is by using dots. Now these dots represent the valence electrons. Valence electron. And hydrogen happens to be the only electron. But in oxygen, these are also the valence. The valence ones. There's 2 electrons in here that are in an inner ring or energy shell you don't see because you're only looking at the valence electrons. So if we count them, hydrogen has 1, this hydrogen has 1, it wants 2 because that would fill up that first energy shell. Oxygen has 1, 2, 3, 4, 5, 6, it wants 2 more. Well, hey, look at this, there's 2 hydrogens here, each with 1. If they share them, now oxygen thinks, oh look, I have 8 now. Each of the hydrogens think, hey, look, I have 2 now, and we're all happy. And that's how we get the covalent bonds for water, to keep water together. Carbon is a really cool one. Carbon has 4 electrons in the valence shell, so it can make a lot of really neat bonds, and that's what makes carbon so cool. Now each orbital, that kind of got cut off here, can hold 2 electrons, right? So it's really easy for a hydrogen, I should have used black, but that's okay, to come along, and another hydrogen to come along here, and another hydrogen to come along here, and then another hydrogen to come along here, and we end up making methane, right? It's cool because it can form up to 4 bonds. Now it can do double bonds, which we'll talk about later, which it'll have fewer things that bond with it, but it's twice as strong as a bond. Well, I don't know if it's exactly twice as strong, but it's a double bond. So when one pair of electrons are shared, that's called a single covalent bond. Now this is kind of tricky because a single bond is having 2 electrons. A double covalent bond has 2 pairs, which is actually 4 electrons, right, that are being shared. 2 from each atom that are bonding together. A triple covalent bond would have 3 pairs. So if we had a carbon, it would have 3 pairs of 3 bonds there, and each one of these would be made out of 2 electrons. Each of these bonds would be made out of 2 electrons each, so 6 electrons altogether. So that's a triple bond. A double bond would look like this, right? With each one of these lines, again, is 2 electrons. One that carbon brought, one that carbon brought. This one brought from that carbon, and this one brought from that carbon. Right? So that's a double bond. It's tricky to remember that double bonds aren't made of 2 electrons, they're made out of 4 electrons, or 2 pairs of electrons. People mess up pretty often. Here's something you should definitely pause this and write into your notes. The number of covalent bonds that different things are capable of making. So hydrogen can make 1 covalent bond, oxygen 2, carbon's 4, nitrogen 3, phosphorus can 5. Phosphorus is a weird thing that it's cool, but it kind of breaks all of our really easy rules that we worry about in biology. When you get to chemistry class, you can worry about why phosphorus breaks crazy rules. For the shape, the shape is really important in biology. So the shapes are what determine a lot of the functions of what molecules do. In chemistry, you'll learn that those orbitals kind of change shape. That's called hybridization. We don't need to worry about that in this class. But what we do need to kind of know is that for carbon, it forms something called a tetrahedron. The reason is because these hydrogens want to be as far away from each other as possible, and the only way they can do that is if they kind of take this shape. And it's kind of hard to draw in a two-dimensional thing, but you can kind of see this one. If you think of this one as coming out at you, this one going out into the screen, and this one right on the screen, and that one right on the screen, that's the way it would look. And here's a ball and stick model of the same thing. It's because those hydrogens want to be as far away from each other as possible, because they're pretty much just positive charges, because their electrons are over here being shared with the carbon, right? So all of these are kind of positive, kind of positive, kind of positive, kind of positive. They don't want to be next to each other. They want to be spread out. Electronegativity is the attraction for a shared electron. So it's a measure of how much an atom wants electrons. Oxygen wants electrons really bad, so it has a high electronegativity. Hydrogen doesn't want its electron. He's fine if somebody jacks his electron. He doesn't care so much. So his electronegativity is really low. The measure of electronegativity and the difference of those measures of the atoms decide whether a bond is shared equally. Right? So if we have something that really, really wants electrons and something that doesn't really, really want electrons, then they don't share them very equally. The one kind of hogs the electrons and keeps them over on its side. If they both have pretty much the same electronegativity, then they share a lot more fairly, and then the electrons are kind of shared more evenly. What happens if they share them really similarly? It's called something called a non-polar covalent bond. So the electrons are all nice and spread out all over the place. If one of them wants the electrons more, it becomes a polar covalent bond where one of them has a little bit more negative than the other side does, and we'll see some of that later. Right here. So here, chlorine and chlorine, since it's the same element, it has an electronegativity of 3, which means this green is where the electrons are. So the electrons are all nice and evenly distributed, right? That's non-polar. If you look at hydrogen and chlorine, hydrogen's only 2.1 and chlorine's a 3.0. So chlorine wants the electron a lot more than the hydrogen does. So most of the electrons are going to go over to this side, which means it's going to be kind of negative. This little squiggly D thing means kind of or partial. Partially negative is what that is. And now since the electrons are being pulled over here more often, this side kind of becomes kind of positive or partially positive. And that's what makes it polar. It has 2 poles, like a magnet has a plus and a minus side, or a battery has a plus and a minus side. And this is kind of what this is talking about right here, about the polar ends having 2 dissimilar ends, like one positive, one negative. Water is a really good one, and we'll talk about that a little bit later. So now, different types of atoms can form ions, and that's something that has gained or lost 1 or more electrons. So if it's gained or lost an electron, it changes its charge. Now if they only have 1 or 2 or 3 valence electrons, they're most likely to lose those electrons. So if they lose a negative, they become positive, and they're called cations. If they have 5, 6, or 7 valence electrons, they're more likely to gain electrons to fill up that valence shell, and they become negative, which is called an anion. So cation are positive because they lost negative charges. Anions are negative because they've gained negative charges. So you have to think about gaining or losing electrons, which are negative. And we learned that electrons are negative. And so you have to think about when you're adding and subtracting negative numbers, what that does to the number. Right? And that's the best way to think about that. Here's an example. So sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, right? No, sorry, 11 electrons. And this one right here is all by itself in its valence shell. This is the valence shell. It's really easy for it to lose that one. Well, chlorine has 1, 2, 3. Let me do it so you can see it here. Has 1, 2, 3, 4, 5, 6, 7. It needs one more to fill up that ring. So it really likes to take electrons. And it can take this electron from sodium, it takes from sodium and kind of takes it for itself. Now, this one, the sodium, lost a negative charge, so it has a positive charge. If it lost a negative, it's positive. This one, the chlorine, got one more negative than it has positive, so now it's a negative ion. So this is a cation, right? And this one is an anion. And the way you write them, sodium is Na, and now it's plus. Chlorine is Cl, and now it's minus. That's how we write it as an ion. So you just use its atomic symbol and then add whether it's a positive or ions have lots of different functions. They're a little bit different than their neutral atoms. They behave differently. They are electrically charged, so that causes a bunch of different things, but their valence shells are full, so they're a little bit happier that way. But they're very, very important in nerve impulses or signals, with muscles contracting and lots of other biological processes that we'll see later. When we get to photosynthesis, ions are huge. Ions can form things called ionic bonds. Ionic bonds, that's when you have something that's positive attracted to something that's negative. It's all based on things, opposites attracting, right? That's something that everybody has heard before. Opposites attract. Well, we get a cation that has a positive charge and a negative ion that has a negative charge, and they're attracted together and they form an ionic bond or an ionic compound. And sodium chloride is a really good one. The one we just showed right there showed that sodium becomes positive, chlorine becomes negative, and this happens. So here goes that electron that we talked about earlier, right over there. Now, this one has a positive charge, this one has a negative charge. They're attracted to each other, they stick together. If you get a whole bunch of them, you'll make a nice big crystal of salt. And oh yeah, sodium chloride is salt. Water, one of the important features of water is that it's a solvent, which means it likes to dissolve stuff. You might notice that because that's what we shower in, right? To try to dissolve the dirt and stuff off of our skin to get clean. We use water because it dissolves lots of dirt and stuff. Right? The stuff that gets dissolved is the solute. There's usually lots more solvent. So if we were to make an inequality, lots more solvent than there is solute in a solution. Much, much more of that. This is the thing that dissolves that. Now, because water is polar, we haven't shown a picture of that, but water is polar because oxygen has a really high electronegativity. And if we have the hydrogens here, right, the oxygen likes to take the electrons away from the hydrogens. So the electrons are going this way, plus it happens that oxygen has some extra electrons over here. So it's negative up here and positive here and positive here. Right? So it really is good at dissolving polar things or ionic substances. That's why salt is able to dissolve in water really quickly. When we take a whole bunch of water molecules and put them around a cation or an anion, it's called hydration. So that should kind of make sense. When we're hydrating as people, right, we're taking in a lot of water. Same thing with molecules. If they're absorbing lots of water, they're being hydrated. Or if they're attracting, this is attracting, not really. Hydrogen bonds. These are really cool bonds, very, very important bonds that actually make it possible for almost all life on Earth. If it wasn't for these, life as we know it wouldn't exist. They're very weak. They're not real strong. They are kind of strong, but they're not strong compared to covalent or ionic bonds. Now they occur when a hydrogen, which is pretty much a proton and electron, when it's in a covalent bond, that other element usually takes away that hydrogen. So hydrogen is pretty much a proton, and it's going to be attracted, so it has kind of a positive charge. It's going to be attracted to something that is negative, right? Or a kind of a negative charge. So the hydrogen bond forms between an atom with a partially negative charge and the hydrogen atom that is pretty much a positive charge. Now, it has to be to an element that's relatively high in electronegativity. Otherwise, it won't take away the electrons as much. Right. Water molecules can attract each other, and it gives us lots of things that we'll talk about next time. So here's a picture of it. Here's the oxygen. That's oxygen. Right. These are the hydrogens. We know the symbols, so I don't know why I'm writing out the whole word, but there's the hydrogens. These are the extra electrons over here that are hanging out in the oxygen, right? So it's kind of negatively charged. Well, since this electron that's being shared here kind of wants to go that way, right? This becomes a positive, which is the way it's labeled, a positive. This positive is attracted to this negative, and it's not really strongly relative to this covalent bond, right? This is a strong covalent bond right here. This is a much weaker hydrogen bond, and it causes water to kind of stick together, which when we get to the properties of water next section, you'll learn why that's. Van der Waals forces, or even weaker forces, they don't even call them bonds usually. In some places you can see them called bonds, but they're usually so weak, they're just kind of called forces. They need to be really, really close together for them to take place. They have to be really, really close. And I said they're weak. They're not as specific. They don't have to be between certain things anymore. What happens is that normally we have the nucleus, right? Let's say here's the nucleus that's positive, right? And there's all these electrons around here, floating around, flying around. Usually they're kind of, we kind of think of them as nice and uniformly around. Well, every once in a while, it just so happens that maybe all the electrons go over on this side. When they do that, that means that here's the positive part. Now all the negatives over here. So this is kind of negative and this is kind of positive. So just for like a split second, this atom kind of becomes polar in a way. It's very, very partial. It's very, very slight, but it ends up causing a slight temporary positive charge on one side and a negative charge on the other side, and it causes a little bit of an attraction, and they stick together. I have a picture, I hope, right here. So here's the typical simple atom, right, just kind of hanging out. Well, all of a sudden all these electrons just happen to cruise over on this side, right? If all these electrons go over here like this, they can actually push these electrons over here. So these electrons that were over there are going to go over on that side, right? And now it's going to be kind of positive right here and kind of negative right there, and there's going to be a little bit of attraction. But they need to be close enough together for it to work. It's like if you have really, really weak magnets, you got to get them close together to be attracted to each other. Really strong magnets, you can have them far away and they'll go and they'll stick together, right? But not in this case, close together. And here's the concepts that we did. There's covalent bonds, ionic bonds, and then there's those weak interactions that are very, very important in science, even though they're not super strong bonds, right? Good job.